the materials. I posted it in the chat, so let me just repost it just in case. So make sure you have that. And for those who have Codio account, if you go to Codio, then you don't have to download anything. Just go to Codio and you would see something similar to what I see here. If you go to Codio, you will see a page for the. So if you go to Codio, you're going to see something that looks like this. Yeah, and then basically you start the notebook on 3A. Okay, so once you hit that, it's going to load the notebook, and then you wait. So if you're using Codio, you don't have much of a struggle compared to if you have your own thing. Okay, so if you have your own file, then now if you're using Codio, just pull out the file that says student file, right? So there's going to be the student IPython notebook. If you pull it out, that would bring up something similar to this. And sorry for the date. Should have changed the date, but sorry for that. So, but the main thing you see is you see the student file. Now, if you are using your own environment, your own Anaconda environment, then you have to, basically what you have to do is go to the location on your computer, the file explorer, go into the location where you see mode 1, mode 2, you do a right mouse click. If you already have Git, which Dr. Musa took us through it, so we should have Git. If you do a right mouse click, if you're using Windows 10, then there's an extra layer. You have to click on new. I think you have to click on show more. They moved it into show more. And you see the Git bash here. Hit on Git bash here, it will give you something similar to this. For me, the fonts are small, so I opened one similar to that, okay? And what you want to do is git pull. I've done modification on my end, so if I try to do a git pull, it's going to give me an error. On your side, you're going to do a git pull. If you do a git pull, you're going to get a folder for mod 3, okay? And that will be the starting point, okay? So in mod 3, you then see the day 1 and day 2. And in day 1, you see this file, the IPython, both the student and the solution. For now, for your purposes, use the student file. Okay, this student file here. Now, the way to start your Python is through Anaconda, which Dr. Musa took us through. You start with the Windows, and then you type Anaconda, okay? And Anaconda Navigator will take you through it. I use the Conda prompt, and the reason for using the Conda prompt is that I'm then able to I'm able to change the different condas that I have and then select one that I want. Okay. In your case, you wouldn't have this problem. You see, in my case, I have different versions, different environments set up. So I'm able to pick one. And then once you do that, you do your Jupyter space notebook. Okay, if you hit, now the first thing you do actually, not Jupyter notebook, is you CD to the location where the file is. Otherwise, you're going to have a hard time finding it once you start Jupyter. Okay, so that's the reason I use this. So you do a CD to the location where the thing is, do a dir, make sure you can see the file, and then you do your Jupyter. Okay, so Jupyter space notebook. Okay, now once you fire Jupyter notebook, it's going to bring you to this page that looks like this. Okay, so you're then going to see the reason why you do a CD is in here is going to be very difficult to go back because if Jupyter notebook starts, the root is where you started, you call Jupyter notebook. Okay, so if your root is not nicely, if your reference point is far away from where your file is going to be a struggle. So I put my reference point close to where the file is and start my Jupyter notebook, so then I can see the files. okay? And once you see the files, you click on the student file, okay? Once you click on the student file, it's going to open something that looks like this, okay? And the way to tell it's a student file is there's going to be a lot of empty slots, okay? There's going to be, and those empty slots are what you are going to try and fill out, okay? So that's the difference between that. Now, so that you don't get too discouraged, because this is a learning process, what we've done is we provided a solution sheet. So the way the solution sheet is supposed to do is supposed to guide you. So as you try your hands on here, if you get an error, then you go to the solution sheet, and the solution sheet is nicely labeled, okay? So if you go in here, it tells you that this is the slide 7 of what Paul took us through. So if you take what Paul took us through, which is the PowerPoint, and you go to slide 7, okay? So I'm sorry, going too fast, but stop me if you have to. You go to slide 7, you'll see the data there. Okay, so we made it so that you can combine the PowerPoint and and some Googling of materials online and be able to go through. Okay, so this is slide 7. Okay, so we will start with making sure that everyone is on the same page. We've been able to clone the repo is the first thing, okay, with a git pull. You clone it one time, and from that point on, which is from the beginning of that class, Dr. Bosa took you through, you're going to just do git pull, git pull, git pull. That's all you do. Okay, so assuming the git pull went through, then, like I said, you're going to have something that looks like this with a day 3 added. You go to your day 3, and you should see that the file is there. If you're not able to do that, then just create a day 3 folder, go to the GitHub, download a zip file. Okay, so let me just do that. I know some students are going to. So you go down here, okay, you do a code, and you can download the zip file. Okay, download the zip file. All right, this is what we did. We just use a git pull, a git pull. With a git pull, you just copy this guy and put it in there. Okay, git pull, you just copy this, and you come down to your console, which will be this guy here. Okay, and so you do a git pull and you paste it like that, and to just pull it. Now, if I try to do it, my repo might be out of, I've made modification, so it's telling me I'm ahead of the head. So, but in your case, you're going to get something. Okay, so are we all set? So you can get a file here, you can download as a zip, and then double click or open it, and just copy and paste the file into the location. So I do this, and I go to mod 3, and I extract just mod 3, because you may have modified mod 1 and 2. So just mod 3, extract it to a location, okay, and extract it to a location that you can get back to. I put it on download, let's say here, and let's say I put it right here. I say, okay, I go to my download then, and I'll be able to then see the file there and take it and drop it where I want to drop it, okay? So that's how you do that. So are we all set as far as that goes? So here, and I go to mod 3, and that's the beauty of Git, that I can just come down here, just copy mod 3 and stick it where it belongs. Or I can just come day 1, copy the files, or even start Jupyter Notebook in here. Just that this is a download location, and so I'm halting this for a moment. So does the audio come through for everyone, please? So I see there's a chat. Someone is saying the audio is not coming through, but so let us know if the audio is not coming through for you. And then there's a second. Oh, cool. So the audio is coming through for at least one person. So then I think the person not getting the audio, please check your audio, Francis. And then can I do my coding in Jupyter instead of Terminal? Yes, you can, which is what I was showing. So you have Cordio or you have Jupyter Notebook. You can even do it in Spider, and you can do it in VS Code. We'll cover this during the TA session. Okay. Okay, cool. So if there are no more questions, then we will, but please keep your chat coming through. If you have any questions, just post it on the chat. Okay, thanks a lot. Not your project location, but you can do that. You can start your Jupyter Notebook here, and when it's done, you move it to where you want it to be. So we are all set. We know how to clone. We know how to get the file, and we are ready to go now. So I'm going to use Cordio, but interchangeably, I'm going to use Jupyter Notebook, just in case question comes up. Okay, so I'm going to use these interchangeably. It shouldn't complicate anything because Dr. Musa took us through. Okay. So now we have access to the student file, and the student file primarily, like I said, contains hyperlinks to the slides. Okay, so once you click on this, it takes you right in. Okay, and once you click on, if you get lost, just come to the objectives, you click and it takes you. So if we recall from the material, just to re-emphasize what Professor Paul took us through, we have data that we want to create samples out of the data. Looking at this data, it looks just like an Excel file primarily, and we want to just pull samples out of it. Okay, let me go up and turn on my audio. Yeah, sorry for this. I thought my audio is on. The thing is, how do we get this data into Python? Once you get the data into Python, these computations are just computations. This is the sum, and this is your numeric, the NumPy array, or this could be your data frame, and this is just a number. So this can easily be implemented in Python. So let's see how we go about doing that. Okay, so the way to do that is, since it's just a 1D array, 1D data, which is more like a vector, I'm going to use a lightweight data type, which is the array. So I'm going to put everything in an array, okay, and that's how you create it. Recall from Professor Musa's class, an array, the square bracket is what gives it away, a square bracket. And then this is a function call. So you take in, this could be redundant, but I like doing that. Okay, so primarily what you are doing here, let's say I open this, is you are saying A equal square bracket 1, 2, 3, something like that. But in my case, my numbers, I have more numbers, so I don't want it to go up the screen. And that is the reason why. So if I do A, then I have that. Okay, and if you say the type of A, we call from Professor Musa's class. So this is a list, and that is why I turn the list into an array, okay, because I want to use some methods. Okay, and now I have an array. Okay, so that's all I'm doing here. So do baby steps. Do baby steps. Start with something small that you can easily comprehend, and then you grow it. Okay, so this, I started with lines. I started with this line, and then I started growing. Once I realized, okay, it worked. Alternatively, what you can do is we have this data. We made Professor Paul gave us a copy of this data, which is here. Okay, so we can use that as well. I don't want to download it, but the data, we have a copy of the data here, which is just a straight Excel. It's just a one column, okay, one column with a variable name on top. Okay, and we call from Professor Paul's, someone said okay, so Nana, could you please help think Zen? So you can actually get that from, let me send you the, yeah, you can get it from the GitHub, or you can get it from the Codio. If you don't have Jupyter Notebook set, then Codio will be the place to go because the files are all there, and all you do, you click on it and you get it show up. Mine might take a long time to start, so I'm just going to go in the interest of time. Okay, so what we want to do is that we can either read the data, okay, or alternatively, so let's try this. Alternatively, what we can do is instead of reading the data that we have, remember, you can always insert a cell and try things out yourself, okay? So we can do this, okay? Proceed and see that you can either load the data, okay, and display it, or you can load the data from the stored data set, okay, that those are all data. And if you do that, you still get the data that looks like what we have. So that's a second way of doing it. You've read the data, and that's a big wow. Once you get the data in Python, then the rest would be much easier. For now, don't worry about this reshape and sheet equal to 0, because the sheet equal to 0 means that if you have multiple sheets, I put it there so that in case you have multiple sheets, i.e. you have this sheet, you have this sheet, then you want to say, I want to put sheet 0. So the data we are using is from sheet 0 instead of sheet 1, okay? So that's what this means, okay? And then we'll reshape it so that it comes out in the form of a nice array here. Okay, so for the exercise, in the interest of time, we then want you to use Paul's slide to compute the mean, okay? Compute the standard deviation by hand, use the notes given on Paul's slide 9, and the reason why we divide by n-1 is explained on Paul's slide. But we would like you to try this, and then we'll get back and then we'll go through it. Okay, there are two challenges. The challenge is that you, instead of just writing this as a sequential formula, we'd like you to do a function so that you can just call a function, just like we have np.mean, and then that we want you to also write a function that would hopefully do this for us. Okay, so we're going to take a quick, so your function is going to be like my mean, say. So instead of np mean from NumPy, it's going to be like your mean is going to be like a mean function like that, so that when it's called on the data, it gives us an output and the same, and then we want you to also plot. So we're going to take, hopefully we're going to give you about 5 minutes, try setting it up, try running it, and then we'll come back. Let's say at in 5 minutes time, this 34, so about just before 1:40, let's come back. Okay, so if anyone has any problem, we can take you through this. We give ourselves 5 minutes, get to a starting point so that when you go home, you don't get stuck. There's also office hours you can utilize, but give ourselves 5 minutes. Let's give it a shot. Remember, there's the instructor file you can look at, but we would suggest, we recommend you try it on your own and then use the instructor file. Okay, so remember the formula is the summation, and the sum is np sum. So you do np sum on this and divide by that this, and you should get that. Okay, for the standard deviation, it's primarily np sum of a mean minus the individual squared divided by 144 minus 1, and then do np sqrt on that. If you're able to get a variance, that's fine. And don't worry about the function. The function will be right. So we take a quick 5 minutes and get back. Thank you. Okay, so Codio. If you're in Codio, all these have been installed, so don't worry about them. Okay, you just go down here, import your libraries, and then you can start. Okay, so like here, Control Enter or run, that loads the data, and then you can just start. Okay, so you can say something like mean. Okay, equal. Okay, and what is the mean? We're going to use MT for NumPy. We do the sum. We call from Dr. Musa. DBT. Okay, and divide by the length. Okay, you can make it dynamic. LN of DBT. Okay, and then of course it's of no good if you cannot print it. And then there we go. Okay. So that should be how I will implement it. Okay. So use the NumPy for the sum, divide by the length, and I'll take it. And the standard deviation, you do the same thing, just take a look at the formula. Okay, so it's always look at the formula and write it out. So the sigma is this NP sum. The mean you've already computed and subtract from each one of this and square. Okay, so you take the NP sum. So let's say my var or dbt okay, 40 var equal, okay, and then do NP sum of, and you take the individual, the mean, okay, so it's dbt mean, okay, minus the individual dbt, okay, and you basically up it up by 2, and if you want to be more specific, you group this guy, okay, and you divide by the length, like we did. LN of DBP, okay, like that, and that. NP dot. It's a method. Okay, well, let's see why this is. I think I'm doing something a little tricky there. It's the individual. You see this type of error, and once you see it, just look at the solution that's been provided. I could have fixed it, but I want you to see that if you go on the literal side, you could get an error. And when you get an error and you are unable to decipher it, then just look at the solution. Okay, so just look at the solution, which would be the second one, to say instructor solution. Okay, so the solutions will be in here. Okay, there's a folder called solution. So if you click on that, the difference between the individual and the instructor is that the instructor one has everything in there. Okay. Okay, so we did a sum, we did a length, and we did a mean, and we got a mean. So here I took it in different steps. Then we got an output. Okay, so you run that, and it says you don't have that because we don't have the data. So you go up here and load your input. Okay, or use the run. The run is much faster. Okay, you do the run, and you then compute your mean here, and that will take you through that. And then the variance, this is what, okay, so it's saying here that instead of summing, we could then take this, which is another data, and then do the sum on the data, and then divide. So let's take that. So you take this guy, okay, Control C, go to the student, and instead of NP sum, you basically say the sum of this. Okay, so add it here, okay, and take out the sum in front here. Okay, so this is just taking you through the baby steps. Eventually, you will figure it out. Okay, so we have this all squared and then dot sum. Okay, so you go back and do that. This all squared. Okay, a square could be up or down. Dot sum and divide by the length, and that will get you that. Okay. There we go. I think I have more. What is this doing here? Sorry. This here, and this, you're also going to encounter these types of things, but once it comes, just take it, look at the solution. So let's try that. Say that there's an invalid. Okay, we go back here. And then, so if you're hopelessly stuck, then this is what you do. You just come down here and take this. Okay, I'm just taking you through. I could have fixed it, but I'm showing you how you can do that. Okay, so you bring it down there, run it, and then if it's all hopelessly stuck, there we go. Okay, so you're going to see these types of things. From the TA session, these are some of the experiences that students do have. So that's why I'm taking time to do that. Okay, so once you do that and it works, then that is a big class that you've accomplished that. So now we've got, and then you take the square root of that. Okay, so in the interest of time, we're just going to go through quickly, and I'll show you how to utilize this. Are there any questions? Okay, so once you are able to compute the variance, then you take the square root of the variance. The square root comes from the NumPy. Okay, so from here, you just put NP square root of that, and that will result in that. Okay, and that takes you through the first part of the try it yourself. Are there any questions? I've provided references here in case you want to, in case the solution doesn't make a lot of sense. You can just open this, and this gives you exactly what we've done with example and a sample code. And this is how we learn from Python. Okay, so this in here they're creating a function, but you don't have to use that function. You can just go down, look at it. That they took the length. They took the sum divided by the length, and then they printed it out. Okay, and so that alternatively you can have you can import the statistic package, and then once you have the statistic package, you don't have to do any of those square root things. The p variance would compute the variance for you as well. Okay, so we have these examples for you to use. Okay, let's go back on the. If there are no questions, we go back to our solution, and I'll walk you through the statistics that Paul computed. So we went through here. We've been able to compute the variance and the standard deviation, and we are able to then print it out nicely, because there's one thing writing the code, and then there's a second thing actually displaying it. So I'm giving you ways in which you can display your output in a nice form using the print. Okay, so if I run this, it shows clearly, I'm telling you that the mean is that, the variance is that, and the standard deviation is that. Okay, the output makes things much clearer. The way you present the output makes things like. Okay, and then when you come to the challenge question is, how do you define a function that will do this? The function, as Paul said, you define the function name, and the argument it takes, and then what the function does, and return the output. Okay, so if I have this function defined, then I can run the data set on the function and get my result. That shouldn't stop you. Once you get your results, what you it doesn't make a lot of benefit. It doesn't give anyone a lot of benefit if you are not able to display the output in a nice form. So I have this, and I've created the results, and I'm going to just print out the results. Okay, so I'm here, and I run that, and then the results come using a function. Okay, and then how do you plot? Paul took us through this. Dr. Musa took us through this. You have the data set, and you just call the plot function on the data set. The plot method comes from the PLT library. Okay, so from matplotlib dot plot dot pyplot, you import from matplotlib, you import pyplot as PLT. That's an alias to matplotlib.pyplot. So then you can call plt.plot on the object, and then plt.show will just show you the output. Okay, like that. Okay, now you can also use seaborn. Okay, if you use seaborn, it's the same thing. Seaborn on the object, and you get an output that looks like that. References are here for you to go through that. If you get down here, then you are through the challenge question. You've successfully gone through challenge questions. Okay, so now we go back to the student. So the next aspect is what the inference portion on slide 12 through 21. So basically, once you get here, the idea is that you then go back to the PowerPoint slide, go to slide 12. Okay, that's the inference portion. And with a video and everything, once you go through, the question then becomes, how do you implement this? Okay, what I see here is I see data. The question is, how do you get this data into Python, and then you'll be able to compute these modes? And so that's what we're going to do in here. Okay, so to do that, this is just a picture taken from Paul's note, but this shows you a step-by-step way in which you can capture data and you can sample from the data. Okay, so I'm using the seed so that it can be repeatable. If I don't use the seed, then my sample is going to change each time I run it. Let's see this. See, when I run it, I'll get 9-0. When I run, I get 5-4. But once I throw in a seed, then it will give me the same thing each time. Okay, 3-4, 3-4, 3-4, 3-4. Okay, so that allows me to repeat my experiment. This is saying from your population, I'm calling this the population is the data. Take two elements from this population. Take it at random. Okay, and so this time it took 3 and 4, and it took 3 and 4, and it took 3 and 4. So this is how you sample. Okay, now we talk about the seed. We're going down here, and then we're going to expand on that. So this was supposed to be your code. So when you go home, you're supposed to take a sample of length of size 12 from the BDP data set. Take 12 samples. Okay, so sample 1, sample 2, sample 3, sample 4, sample 5. Each time you get a sample of size n equal to 5. Okay, so we use a loop. Now let's see how that is implemented. So to implement that, what we do is we take, we are here, okay? Anytime I say take a sample of size n equal 5, see what will happen in here. This is saying, well, you know what? I'm going from 1 through the length of the data. I want to look at all the data. Each time I'm going to take the index. Okay, so let's print the index, what the index will give us out of here. Okay, now once I print the index, then I'm going to use the index to sample. Okay, so give me that. Okay, because I don't okay, so that's what the index do, is return the index. So now I can now run the index on BDP and I'll get values. That's it. Okay, so these are the index and these are the, sorry, these are the index and these are the values. Okay, these are the index and these are the values. That says that when you look at the BDP data set, which is this big data, when you throw it in a vertical form, you take samples from each of the index provided, and then you put it in as an array or a list. Okay, and that is what this guy is doing. Okay, so each time I take a sample, I get a list. I take a sample, I get a list, okay? And these lists, then I'm going to put them together in a nice form. And that is what Paul did. So here, I'm throwing a loop around it so that each time the list is generated, I print it out, okay? And that gives you this nice output, okay, which is similar to what Paul provided on slide 16. Okay, so now you've been able to get the data. Okay, so then we can easily compute the mean of each of these then, right? So we have a list and we should be able to compute the mean of each of the lists and stick it next to it. And to do that, this is how we do it. The print is a way to go. Okay, the print is a way to go. So let's run that. We have the sample that we've taken, okay, of size n equal to 5. We're looping through how many times, and each time we take the sample, we print it out, and also we compute the mean. Let me expand this a little bit so that we see. So we also compute the mean of the sample, and that's the only trick there is. And then I display my index, and then the list and the mean tagged onto it. Okay, and once I do that, I have something that looks like that. Okay, and this looks very similar to what Paul provided in here. You have a sample of size n equal to 5, and you display the sample and the mean. Okay, this comes to creating the bootstrap sample. Okay, so that is the main thing. I think, like I said earlier, is getting the data into Python and knowing when to use a list, when to use an array, when to use a data frame, which was covered last week. Okay, this just re-emphasizing that it can be done. Okay, so now I have my data, I have my mean, I got my sample. So then I can compute the statistics on slide 19 that Paul talked about. Okay, and so all it is if I have a list, sample 1, I have another list, sample 2, I can compute the mean and put it sample 1, compute the mean, put it in sample 2. Take the length, and then I can compute any statistic I want. Okay, so SEM by the formula given on slide 19, and then it's computed. Then the challenge we have to display. We display using the print. Okay, so if I run this, then I'm going to get a sample, the size, the mean, and then the SEM for each of the sample. If I can do it for this a small sample, then I can do it for the bigger sample. Okay, and I can even do more. I can tag on what the upper and the lower bounds are, and then I can now display it. Okay, so that takes us through the confidence interval for slide I think it was on slide 20. Okay. We're running slow on time here. So now I've computed all these statistics, okay, which then brings me very close to what Paul has in here, or Professor Paul has in here. I computed the mean, I computed the SEM, I computed the lower and the upper bound. I can display this one if I want, but I've gotten these statistics and basically constructed 95% confidence interval, okay, using Python. And those are the standard error of the mean. Okay, so I have that. Oh, sorry.
Yeah, William. I think so if you can maybe wrap it up in the next 30 seconds so that we can. I mean, whilst I'm on it, so we have all of it. There's a database called All of Us. So we have someone come to speak to us about it. So if you are on this and then you want to know about it, I think we are going to send the link in the chat area. Start at 2 p.m. I know it has been a long day, but if you are interested, you want to join, feel free to do so.
Okay, thank you, John. Yeah, so this actually is supposed to be something you do at home. So please go and complete the student file, okay? And as you get stuck, please take a look at the instructor file. and things are nicely labeled. So just go through it. We have office hours, so we'll be available to help you through this, and then we have office hours on Saturday. And so this primarily takes you through everything that Paul did today, including the jackknife and all the other computations. Okay, thank you, John, and I'll pass you back to John.
All right, so let's all of us thank Paul and William for an excellent.
Yeah, so I think it's almost 12. So I don't know, John, if we want to take, let's say, a few minutes break and then come back to the video. Yeah, so I'm let's see. Yeah, so why don't we stretch out a bit? So we started at 11, right? Normally, do we go through? Yeah, let's take 5 minutes break. Let's say 7 minutes break and then come back at noon, and then we'll continue with the second slide. So I'll stop here, and yeah, let me bring this other slide on and get this ready. See if I have, yeah. So let me bring this guy on. So this is going to be the part, yeah, the 3D. So this is what we're going to watch once we come back. Oh, John, yeah. So John, do we get them and come back at noon?
Yes, let's do that. Let's
okay.
First we get the second set of slides ready.
Ready. Okay, thanks.
Yeah,
thanks
so again, as you wait, this presentation, this was done in the spring. This was done over 4 days, but we have only two days for the pre-training session. But all the recordings are there. You can review them over your leisure time, and then if you have any questions, you can send those to me or William. So yes, let's take 5 minutes break and then reconvene at noon for the second set of slides.
Okay, yeah, thanks a lot, John. Very well. Yeah.
Did a call with Matt happen?
Oh, sorry.
Is there a call with Matt? Did that happen? Is that
No, I think where he pushed it to later.
okay?
Yeah, like 4.
Very good.
Yeah. Okay, 12 noon. Okay, so I want to if I can find my there we go. Okay, so I'm going to start the session now. It's 12 noon, and if for any reason you can't hear it, just put it in the chat. Okay.
I'll hand over to Paul and William. So over to you, Paul and William.
Okay, thank you. Today I want to focus on linear regression, and I want to look at it, or actually 2 different uses of it. So we're going to talk about multivariate models, what we mean by an interaction, and then I want to focus on predictive modeling, what I refer to as predictive modeling. I have just a couple of slides to talk about multivariate models and what we mean by that. And then I want to look at regression, doing hypothesis testing with regression. And then in the second hour, I want to go through an example of a study that we did recently and look at some of the complexities of developing a predictive model with real data. So as you recall from last week, when we talked about linear regression or general linear models, we're talking about looking at means. So our dependent variable or outcome variable is a continuous variable. And when we do what's called ordinary least squares regression, we're basically looking at the dependent variable as a function of some independent variable or covariate or a set of independent variables. And so we looked at a couple special cases of linear models where if we have just a simple linear regression where our x variable is a dichotomous variable, which we will code either 1 or 0, that's essentially a t-test. And then if we have a set of independent variables that are all dichotomous variables or maybe categorical, maybe they have more than 2 categories, then we have what's called a factorial analysis of variance. And then if we have a mix of categorical variables and continuous variables, then we would, we call that analysis of covariance. So a distinction that I want to make these are sometimes used interchangeably in the literature, but they actually in statistics have a different meaning. When we talk about multivariable regression, we're talking about one outcome variable and we have then potentially multiple independent variables or multiple predictor variables of our outcome. When we talk about multivariate regression, what we mean or what is meant by that is we have multiple dependent variables. And I'll give an example of that. And so that's referred to as multivariate analysis of variance. And then we need to, when we talk about linear regression, doing analysis of variance, or we need to talk about the concept of an interaction. And what is meant by interaction in linear regression is that the effects of one independent variable are not the same across levels of another independent variable. If they're the same, then we have what we call a main effect. There's no interaction. And then we can have, there's a couple of different kinds of interactions, what's referred to as an ordinal interaction or a disordinal interaction. And I have just a couple, or just a slide here of just examples. So if you have no interaction, what you're going to see if you have comparison groups and over time or some other variable like age, maybe, the lines will be essentially parallel. If we have what's called an ordinal interaction, then that's our starting point or maybe our ending point. Our comparison groups are essentially at the same point or very similar, start out at similar values, but then they digress in at different rates. They may not necessarily be, as I've illustrated here, one increasing, one decreasing. They might both be increasing, but they're increasing at different rates. And then the disordinal interaction means that they not only do they end up at different places, but they start at different places as well. So this is what we mean by an interaction in linear regression. And if the interaction is significant, then the main effect can't be interpreted directly. Now, that's generally true, although if the interaction is significant, maybe the main effect can be interpreted, but it can't be interpreted apart from the significant interaction. Usually we look at two-way interactions in linear regression. And if we, theoretically, we could look at any kind of n-way interaction, but then it becomes really difficult to interpret. And usually you don't see more than two-way interactions in the literature. Even getting the three-way interaction gets really difficult to interpret. And if you have like a lot of different variables and you get to like a four-way interaction, then it's almost impossible to interpret. So I want to go back to our cholesterol variable that we looked at last week, and we looked at the linear relationship between cholesterol and age, or age as a predictor of cholesterol. But in that data set, we also had a variable weight in kilograms. And so what we're going to do now is we're going to look at both age and weight as predictors of cholesterol. In other words, we're going to have a multivariable linear regression. And as you recall, or if you don't, you can go back and look at last week's presentation. We looked at cholesterol as a function of age, and we had a regression equation of 102.6 plus 5.3 times age, which we interpreted as for every year increase in age, the level of cholesterol goes up by 5.3 units. And so what I've printed out here is the output that you get when running this, this regression. Now, the format that you see it in here might be different, or probably is different from what you'll get running it in Python. But I want to go over the essential elements of regression output. And so you see that our first table here has SS, which stands for sum of squares, which you remember last year I went through how we can partition the total sum of squares into the regression sum of squares and an error sum of squares or a residual sum of squares. And so here we have the sum of squares due to our model. In other words, sum of squares due to the impact of age on cholesterol. And then we have our error or our residual sum of squares. And then we have a degrees of freedom associated with each of those. And if we divide the sum of squares by the degrees of freedom, we get what's called a mean square, or in other words, that's like an average sum of squares. And so if we look at the model sum of squares divided by the residual sum of squares, we get an F statistic, which, if you recall, that's one of the theoretical distributions in hypothesis testing. And so an F distribution actually has two sets of degrees of freedom, one for the model and one for the residual. And so that's why you see here an F with 1 and 23 degrees of freedom. And if you divide the model sum of squares by the residual sum of squares, you get this F statistic. So the 53.96 here is 101,932 divided by 1888. And then we can look that up in a distribution table, or do it you know, in a program that gives us the probability. And so here the probability of this F statistic being less than or equal to the 53.96 is very, very small. So we have this is our p-value here for this particular analysis. But in doing predictive modeling here, so we're looking at cholesterol predicted by age, what's really important to look at is this R squared value. And you remember from last week, the R squared was the sum of squares regression divided by the sum of squares regression plus the residual sum of squares. And so the R squared value we interpret as the percent or the proportion of variance that are of variance explained in our outcome variable, in this case cholesterol, by our independent variable, in this case age. So here you can see that it's pretty high. So we have 70% of our variance in cholesterol is explained by age. And there's also, in most outputs, they do an adjusted R squared. What they mean by that, this is adjusted for the N. So if you have small n, this is usually going to be less than the actual R squared. As the number gets really large, then it's not going to make much difference here between the R squared and the adjusted R squared. And then there's this root mean square error. And this is just the square root of the error sum of squares, or the residual sum of squares. So this 43.46, that's just the square root of 1888. And then the second table is our regression table with our regression coefficient, the constant. And so you can see here that we get our constant at 102.6 and our regression coefficient of age of 5.3. As we've said before, that tells us that for every 1 year increase in age, cholesterol goes up by 5.3 units. And then the regression coefficients, we can test for statistical significance by using a t-distribution. And so you can see here, this is the probability, the p-value for each of these. So obviously age is a significant predictor of cholesterol in our little data set here. And then we have the 95% confidence interval for the regression coefficient and for the constant. And what we see here is that if we have a statistically significant coefficient, then the confidence interval is not going to include 0. If it does, which will likely happen if we get a non-significant p-value here, is that this confidence interval will go from minus something to plus something, which tells us that it includes 0. So that means that from a statistical standpoint, the regression coefficient here is essentially or is statistically 0. But in this case, neither one includes 0. So what this tells us is that in the population, our regression coefficient for age could be between 3.8 and 6.8 if we were to do an infinite number of random samples. And that 95% of the time, this interval would include the true population regression coefficient. So that's our simple linear regression model. And so what we want to do now is we want to look at a multivariable model, that is where we have more than one independent variable. And so we're going to look at cholesterol as a function of age plus weight, but then we can also look at age plus weight plus the interaction of age and weight. And so when we do that particular model, this is what we get. So we have the same table here with our sum of squares, our mean square, our average variability related to our model, and the average variability related to the error or the residual. And just as we had the F statistic, the probability of F, and then again, we get the R squared values. So now this is where we can determine whether adding weight to our regression equation really adds anything or helps us better predict cholesterol. And so you can see that the R squared, is essentially the same as before with just age. It's about 70%. It's a little higher, but not that much. And then if we look at our regression table, we see that the regression coefficient for weight, 0.42, is not statistically significant. And then over here, you can see that the 95% interval includes 0. So this is telling us that weight probably doesn't add much to our prediction of cholesterol because our R squared hasn't changed very much. And we have a non-significant regression coefficient for weight. If we kept it in our regression equation, then this is what it would look like, would be the constant plus 0.42 times weight plus 5.22 times age. And you notice that our regression coefficient for age didn't change very much. From just age by itself, it was like 5.23. Now it's about 5.22. So weight isn't really making much of a difference in our prediction equation of cholesterol. And there's actually a statistical test you can do to see if the change in R squared is statistically significant. From my perspective, this isn't probably really worth the time to do it. You just eyeball what it is, and you can tell whether it's making a big difference or not. So like if this R squared had gone up to 0.8 instead of 0.7, then weight would have been having a real impact on our prediction of cholesterol, and we would have probably found a significant p-value here for the regression coefficient and kept weight in our model. But because the R squared hardly changed at all and our regression coefficient was not statistically significant, we can go with the simpler model of cholesterol as being a function of age. So what if we look at the interaction of weight and age? Then if we add this, put this in our model, well, we have the same way of interpreting here whether there's a significant interaction. And so again, we'll look at our R squared value, and we see again that it didn't change very much. It's still about 0.7, maybe 0.71 now instead of 0.7. So that hardly changed. And then our interaction here is not, whoops, let me go back here, is not statistically significant. So we can conclude that there's no significant interaction of weight and age. That is, weight isn't changing with or isn't different with different ages as far as predicting cholesterol. So we then conclude that our best model is cholesterol just as a function of age. Okay, so then the next data set that I want to look at is our blood pressure data set that we had last week. We looked at the distribution and used our blood pressure for as an example for a simple t-test. But here I've added some additional variables. And so what we want to do now with we want to have a linear regression model. We want to build a linear regression model, but now our focus is on hypothesis testing, not particularly predicting blood pressure. And so we have a variable here, drug, that I've just called drug A and drug B, and how I've coded those as drug A is equal to 1, drug B is equal to 0. And so in addition to our two groups here that we're interested in comparing with respect to lowering blood pressure, are age and sex. Age, again, is in years. Sex, because it's a dichotomous variable, we've coded at 1 equals female and 0 equals male. So this design we would call a non-randomized comparative effectiveness. And our outcome, in this case, diastolic blood pressure, obviously is a continuous variable, so we're going to do linear regression. And our research hypothesis then is drug A superior to drug B in reducing blood pressure? And then conversely, our null hypothesis would be that there is no difference between A and B with respect to reducing blood pressure. And the reason that we have age and sex in here is because we have a non-randomized study. If we if we had a randomized study, then we could just directly compare A and B with a t-test. But because it's non-randomized, there might be some other variables that affect blood pressure or confound any difference between drug A and drug B. So the first thing that we do in this case is, well, and actually really any case, you want to look at the covariates or the in relationship to your primary variable that you're interested in. So in this case, we want to look at the distribution of males and females in drug A and drug B, and we want to look at the distribution of age in drug A and drug B. So you can see that there's not an equal number or equal percentage of males and females in drug A and B. It's kind of reversed. So in drug A, there are about 55% are females and 45% are males. And in drug B, there's a smaller percentage of females than there are of males. So we have some difference there. And so you can see that in a non-randomized study, you likely get differences like these, whereas if we had actually randomized to drug A and B, this should have been pretty much equal. And then in age, we see there's quite a difference here. There's like an 8-year difference between the two groups. So that the patients or the subjects that are in the drug A regimen are about on average 8 years younger than B. So here we have two covariates, two variables that potentially are going to confound the effect of drug A in comparison to drug B. But this is sort of the first step in actually doing any studies. You want to look at just descriptive distributions of your covariates or your independent variables in relationship to your primary comparison groups. Okay, so as I mentioned, there's potential for selection bias. So the question that we would ask, maybe are drug A patients older than drug B patients? Well, we saw that that they're actually younger than drug B patients, quite a bit younger. And so in our regression model, we're going to include age, sex, and race, but we could include other factors as well. So maybe we have a study where we will look at some comorbidities and their effect on the outcome, like diabetes or hypertension or something like that. But for our model, we're just going to look at age and sex. And so our model is going to be blood pressure as a function of the drug group, which is what we're primarily interested in. But we're going to have to also include in our model age and sex, and then the interactions of drug with age and drug with sex, okay? Because those are potential confounders in our comparison of the two drug groups. So here's our output for our first go with the model. And so you can see that we have the results here that, and as far as the interactions, that's the first thing we want to look at is our drug by age and our drug by sex interactions. And so we can see that neither one of these are statistically significant. The confidence intervals include 0. So based on this, we can drop these from our model since they're not statistically significant. Now we also have an R squared associated with this model, but when we're doing hypothesis testing, our focus is really on what's statistically significant as far as our regression coefficients are concerned, not so much the R squared. Whereas if we're doing a predictive model, we want to predict a particular value, then our R squared is our primary statistic that we want to focus on, and whether that changes depending on what's in the model. So we're going to do another model. We're going to rerun it without the age interaction, and then we're going to rerun it without the sex interaction. Or maybe I did it the other way, I don't remember. But so anyway, yeah, so here is our model run without the drug by age interaction. And so we just include the drug by sex interaction, and we keep age in the model, but not the interaction of age and drug. And so we can see again that the interaction here is not statistically significant. The confidence interval includes 0. So we can conclude that probably we can drop drug by sex interaction. And then so what we're going to do next is we're going to rerun the model with the age interaction. And so now you see that we have a significant interaction. Also, our main effect for sex is significant, as well as the drug coefficient here is significant, indicating that we do have some difference between drug A and B. But because these are statistically significant, we're going to need to keep them in our model. So what we see here, that we have negative coefficients for drug and a negative coefficient for sex. And you can see then that in the confidence intervals here that neither one of them includes 0. They're all on the negative side here. So how do we interpret this? If we wanted to predict blood pressure using this model, what would we have? We would have the constant here of about 84. Then it would be minus, say, 25, depending on the drug that we're A or B that we're interested in. So remember, we coded drug was 1 or 0, and there's a reason for doing that because it makes it easy to interpret the coefficients. So if we're talking about drug A, then we see that what we would do is we would subtract 25 from 83 or 84 here for drug A. If it was drug B, then remember drug B is coded 0, so it would be minus 24 times 0 or 0, so we would have no effect here. And then with sex, you can see that we have a negative 3.35. So remember that we coded sex as 1 equals female and 0 equals male. So if we had an individual here who was in drug A group and female, that we would have 84 minus 24 minus 3.36, okay? And then if, to include the interaction, then if they were in drug A, then we would have an additional 0.23 times the drug code, which is either 1 or 0, and their age. So you can see if drug is B here, that's 0, so this would not be included. But if we had, say, an individual who was in drug A group, was female, then we would have this 80, our constant 84 minus 25 minus 3.3 plus 0.23. And that accounts for the interaction between drug and age. Okay, and again, we don't have particular interest in looking at the R squared here, unless this would be, near 0 or extremely small, say less than 0.1. Then we would realize that the model we have here isn't really worth much. But as I say, when we're doing hypothesis testing, what we're primarily interested in here are the p-values for our regression coefficients. And so
Hello, Paul.
yeah,
Yeah, not to cut you out, but I think there's a question from Finjan on the chat. There are a couple, but this is more relevant. So that
okay. So do you want to go back a slide?
No, so on the chat. So
Oh,
if
okay.
you look in the chat, yeah.
Oh, okay, okay. So when you have the drug by age interaction, yeah, oftentimes age is left in the model, but you don't have to, because it's accounted for in the interaction term. Now we do need to keep sex, in this case, sex in the model, but when you're looking at interaction terms, we typically don't need to include, in this case, age in the model, but we could. But then it then is going to be more difficult to interpret. But I don't know if that answers the question. But actually, what you can do is when you do this exercise, include age in the age, sex, and drug by age model and see what happens. Okay. Was there another one? Oh, let's see.
There are two, but those are from me. Yeah, so
Okay, the difference between prediction and forecast. Well, that's, at least in my mind, that's pretty much the same idea. We're looking at predicting an individual value when we do when our focus is on predicting a value, whereas in the example that we're doing now, we're really more interested in comparing the drugs than predicting an actual value for any particular patient. And let's see. Oh, sure. Okay. Yes. So the BIC and the AIC, the information criteria, yes, that's often used to determine which is the best model. The problem with automated statistical tests, such as either forward selection or backward selection, which I'll get to in next hour in my example, is that that's really an invalid way of selecting variables for a model. And there are a number of reasons for that. There's quite a bit of literature on that, but that's used in almost every statistical package, is the forward, backward selection, or backward elimination, forward selection. If you do use that, it's okay if you have a few variables. If you have a lot of variables, then it's not okay. Let's see, was there another question?
no, I think that's it.
That's it, okay.
Thanks.
Okay. So then what should we use? Is that related to model building, I guess?
I guess, yes.
Yeah, okay, so I'm in the next hour, I'm going to give an example of the more modern way of determining variable selection for predictive models. But for the time being, just realize that sort of the traditional forward selection or backward elimination have been shown to not be really appropriate. And the reason for that is that you're using p-values to determine what goes in and what goes out. Sure. So that's the thing about when you include interactions. If the interaction is significant, then it's possible that the main effect may not be, but that doesn't really matter. It's in looking at the coefficients, if the interaction is significant, then it doesn't really matter what the main effect, whether that's significant or not. And we could probably drop the main effect if we and come out with the same conclusion. But that's kind of one of the issues of when you start to look at interactions. You have to kind of be careful of what you or I guess be careful of how you interpret that and what it might mean. But let me continue here. And so in my model, then I have in my first table here, I have just the observed blood pressures between drug A and drug B. And so you can see that drug A is the better drug as far as lowering blood pressure by about eight points. Okay, but here, because in our model we had effects related to sex and an interaction of age and drug, our predicted values, mean values, are different. So for example, if we have, say, patients age 50, then there's a difference between males and females. You can see the males have a higher value of blood, for blood pressure. If we increase age to 70, you see that we have higher blood pressures here related to age, but we have about the same difference between males and females. But for drug group B, regardless of age, the average predicted blood pressure for females is 80. For males, it's 84. Now, to really understand this and get a picture of what's going on in our example here, what we do is we graph the predicted regressions. And so, if it'll change here. Yeah, so there we go. So here are the predicted regression lines from our model that has drug as a function of age, of sex, and age by drug. Okay, so you can see that for drug A, we have the effect here on blood pressure increasing with age. Okay, but for drug B, we have a constant basically across regardless of age. Okay, so these represent the means that I had in the previous table. So our conclusion here, which turns out to be a little more complicated than just is there a difference between drug A and drug B? Well, it depends on age as far as drug A is concerned. So you can see that with increasing age, the effect of drug A kind of disappears or starts to wane. So, but with drug B, it's higher than the overall level is higher than drug A, but it's constant across all age. It's affected by age. And so our conclusion might be, rather than just, drug A is better at reducing blood pressure than drug B, we would say that it's better than drug B for the younger patients. But as a patient is older, then the effect of drug A begins to disappear and become fairly similar to drug B. So that's looking at the interaction then between the drug and the covariates in a non-randomized study, and why you sort of need to really kind of, in a non-randomized study, really think about the effect of the covariates. Now, if as I say, if it had been a randomized study, we could have just, that would have supposedly washed out any differences related to age and sex between the two drug groups, and we could have done a t-test. Let me go back one slide here. So we could have just done, if neither interaction had been significant, or either the main effects of age and sex, then this would have been the comparison we would have done with a simple t-test and concluded that drug A is better than drug B. But it is better than drug B, but it's better for younger patients than it is for older patients. Okay. So I want to just mention briefly here multivariate analysis, where we have multiple dependent variables now. We can have multiple independent variables, but the difference here is that we have multiple dependent variables. In other words, we have patient has the same patient or the same subject in our study has different outcomes from maybe the same survey instrument, or maybe the repeated measures. But the example I want to give here is comparing mitral valve repair with mitral valve replacement. And so we did a study some years ago looking at quality of life, or health quality of life, using the SF-36 domains, which have 8 different domains, like physical function and so on. And so this is multivariate because we have 8 different outcome variables rather than just one outcome variable. And so what we want to do is we're going to do what's called profile analysis. We want to test the profiles of the 8 domains from the SF-36 by our 2 independent groups here, repair and replacement. And basically what we do is we test for the interaction between profile and group. And if it's not significant, then we can interpret the group main effect as differences between profiles. And so this is what these are the domains of the SF-36, measuring different things related to physical, social activities, general health, pain, and so on. And so this is what we get actually doing 3 different measurements at baseline, 1 year post-surgery, and then 4 or more years post-surgery. And so you can see that what we have here is essentially parallel profiles. In other words, we have pretty much the same profile, except at baseline and 1 year post-surgery, the repair group has higher scores. And for the SF-36, higher scores mean better quality of life, have higher scores than the repair or than the replace group. But as far as the domains, they look pretty much, or the difference here is pretty much parallel across the domains. And the same thing for 1 year post-surgery. But at 4 years post-surgery, we see that we still have essentially the same profiles, but now there's really no difference between the groups. So this was actually quite a complex interaction, because we looked at not only differences in profile, but differences over time as well. But this is an example of profile analysis where you have multiple dependent variables. Okay, so I'll stop there with that portion. We'll take, I guess at this point, a 10-minute break. And then when I come back, I'll spend the next session looking at a particular study that we
So we want, I don't know if we want to take a break because it's almost time. So we want to at least get through this session. Give me a second. And let me see if I can get to, yeah, here.
Independent variable. And it's possible that you can have,
Let's see if I can get
there
there.
were a number of issues in hypertrophic cardiomyopathy registry, or HCM. And so the focus here was predicting atrial fibrillation from a set of covariates or models. And so there were a number of issues in this study that we had to address in doing the analysis. And I wanted to use this as an example of, I guess, maybe a really complex analysis, or what turned out to be fairly complex. Every study you do might not be like this, but just to give you an idea of what's involved in data analysis, that is not just setting your data up and running a statistics program and getting an answer. So the issues that we are going to look at here are issues related to missing data, how we select variables for our model. Because our data is time to event, then we have to look at the phenomena that's referred to as competing risks. And in our survival model, or time to event model, I mentioned the Cox proportional hazards. So in this case, we have to deal with non-proportional hazards. We actually have multiple events because, as you obviously would surmise, that patients can have more than one AFib event over a certain amount of time. And then once we get a model, then we have to look at how well the model discriminates, how well it calibrates, and give some sense of whether the model is valid or not. So to start out with, our hypertrophic cardiomyopathy was an NHLBI sponsored study, and it was recently published in the Journal of the American College of Cardiology Electrophysiology last year. So the registry included patients with a diagnosis of hypertrophic cardiomyopathy. The age range was 17 to 67. Many of the patients were fairly young because HCM does affect younger individuals, probably more than older individuals. So we enrolled patients from 2014 to 2017. We ended up with 2,755 patients in the registry. These patients came from 44 different healthcare institutions in 6 countries in North America and Europe. Follow-up is actually ongoing. The study is not finished yet. We're at, actually, I think right now we're over 4 years of follow-up, the average follow-up. And the primary outcome that we're interested in is sudden cardiac death. Now, fortunately, I guess sudden cardiac death is not a real common occurrence. So in order to do the analysis, it's going to, of that particular outcome, it's going to take a while to get enough events, for enough events to occur. But a secondary outcome that is of interest is atrial fibrillation, or AF as it'll be abbreviated. So the first issue that we had to deal with is missing data. And anytime that you do research involving human patients or human subjects, you're going to have missing data. It's just There's just no way around it. But the issue is that missing data may influence the results of a study. Now, if you have 1% or less of a sample that has missing data, then, or some people say if you have less than 5%, then just drop the missing data from the analysis. It won't make that much difference. And that's probably true. But if we have a fair amount of missing data, then we may need to do what's called multiple imputation to produce complete data sets for our analysis. Now, if you have a study where you've got 40 to 50% missing data, then even doing imputation is kind of questionable. In large studies like this, every effort is made to obtain the data to get the data, but it's just impossible to get complete data when you have large studies like this. So we need to consider the reason for the missing data. And so we have different categories of missingness. And the first one, what's known as missing completely at random, means that missing data is not related to the outcome or any of the covariates or independent variables in your study. That's pretty rare to actually have happened, but anyway, if you have missing completely at random data, then you can ignore the missing altogether, regardless of how much there is. Then the concept of missing at random means that missingness or the mechanism of missingness is not related to the outcome, but it might be related to the covariates. So for example, you might have missing data is related to maybe age or maybe gender or something like that. And then the last category, not missing at random or not ignorable, means that missingness is related to the outcome and probably to the covariates. Now, the thing about dealing with missing data is that you really never know for sure which is the correct assumption. However, if you're assessing an outcome longitudinally, then it's not likely that your missing data is missing at random. So an example that I think I talked about last week, the Courage trial, where we assessed quality of life at baseline and then up to 12 every 1 month, and then every 3 months, and then 6 months at 12 months, and then yearly thereafter. So, and it turns out that some patients were followed out to 6 years or 72 months. And so what happens is that you have fewer responses to your quality of life survey over time. And what would be the most likely scenario is that over time, the patients who are less well are going to drop out of the study. Patients are going to die. And so over a long period of time, you're going to have the healthiest patients that are likely responding to your survey. And so in that case, it's the reason for there being missing data is not ignorable, that it's related to a patient's health. But we, like I say, there's no way of being certain why data is missing. But when we do the analysis, if we do have missing data, then we're going to have to make some assumptions. And so in this particular application here, we assumed that data was missing at random. I'll give some examples of that, of why that may not be entirely true. But anyway, what we do then is we're going to generate some complete data sets. And typically 3 to 5 is the number that's been kind of arbitrarily established as how many you need to do In some cases, you might need to do more. But we're going to impute the missing values, and we're going to basically do that by regression, so that we have a certain number of complete data sets. Then what we do is we analyze whatever our analysis is, each set individually, and then we're going to combine the results to get estimates of our regression parameters. And so the regression parameters, whether we're doing simple linear regression, or in this case, we're going to do Cox proportional hazards regression, we just average each parameter over however many analyses we did. However, when we compute standard errors, we have to take into account both the variability within each data set and variability between data sets. So that's a little more complicated, but because we're imputing missing data, that is, we're estimating what the missing data might be, we have to account for both within and between variants. So there are different ways of doing this. What has been done in published studies, which is not a good idea, is just to do what's called simple imputation or single imputation, where you submit like a mean value, or you substitute the mode if it's categorical data. That's not a really good idea. What we used in this study for our continuous variables was what's called predictive mean matching. And basically what this does is we make random draws from the observed values that are not missing, and then we substitute that particular value into the missing. And so you can see why we're doing this several times, because when we draw at random from the observed cases, we're not going to get the same value every time. But the one thing about predictive mean matching is that we'll always get a value within the range of observed values. Whereas if you use a theoretical distribution, like a normal distribution, you could get values that lie outside your observed range. So, and then for dichotomous variables, we're going to calculate a probability based on our observed values from a binomial distribution. So this is the basically the methods for doing multiple imputation. And so I wanted to give an example here of the different variables, or some of the different variables, and the amount of missing data that we had in the data set. And so here I have a set of variables. So here's demographics, age, sex, race, BMI, and we have comorbidities, history of heart failure, history of stroke, and so on. BNP and troponin are what are called biomarkers, and then the last set here is genetic variables. And so remember, we had 2755 total patients, and so this is the percentage of missing for each of these variables, and you can see it ranged from less than 1% to about 5.5% or 4 or 5% for some of the genetic variables. And so these are some more of the variables. So the magnetic resonance variables, left ventricular mass, right ventricular mass, and so on. The amount of missing is a little bit more. It's about 6%. And then this is the last three here, what's called morphology, about 4.5%, a little more. And you can see that in this case, the percent of missing is all the same because a patient's value for these variables like mass and mass to volume ratio, ejection fraction, come from getting one scan. So if they're missing the scan or the missing one, then they're be missing all of these. And the same thing with morphology. So it turns out that for the variables that we were going to look at as far as predicting atrial fibrillation, all of them were missing less than 7%. Doing multiple imputation then would be a way of handling the missingness, because the missingness wasn't. I mean, it turns out to be extensive because there are a number of patients that have missing values, but for any one variable, it was less than 7%. So what we're going to do, and I'm not going to go into any more detail on this, but what we do is that we build data sets that have no missing values using our imputation methods. And so I did 5 data sets where I imputed values to missing data in the order of how much missing there was. So I started out like with age and sex, which had less than 1%, and then I did another 5 where I randomly imputed without regard for how much missing there was. So I ended up with 10 complete data sets. And then so every analysis that we're going to do, we perform 10 times. And then we estimate the regression coefficients by just averaging those over the 10 data sets. But then I've put this in for estimating standard errors to show you that it includes both within variance for each data set and between variance or variance between the data sets. Okay, so it turns out that for our analysis, there were some patients that were not were excluded, and there were 77 with permanent AFib, so those were excluded. And then it turns out there were 47 that had either no follow-up or a few that were missing values for all 46 variables. So that left us with 2631 patients for analysis. 96 of these patients had an AFib event for a total of 127 AF events, and there were 24 deaths from any cause in the follow-up time that we looked at. So we have 10 complete data sets. There's 2631 in each data set with complete data. And so we're going to analyze each one of those separately and then combine the results to get an estimate of the regression coefficients. So our outcome is a time to event. So we have atrial fibrillation, which is just yes or no. You either have the event or you don't. And then the time from enrollment in the study to the event. So our analysis is going to be Cox proportional hazards. And we have 46 potential predictors of atrial fibrillation. So now we have a lot of variables. And so the question is how are we going to select out of the 46, which are the best predictors of AFib? If we do ordinary regression, as you probably know, you really need more subjects than you have variables. And kind of a rule of thumb is you need about 10 to 20 subjects per variable. Ordinary least squares regression, as as I mentioned earlier, relies on statistical significance for variable selection. That is, it either forward selection or backward elimination, but that's based on a p-value that you set for either inclusion or excluding. A newer method for selecting variables, which you are seeing a lot more in the literature now because it is really an advantage to the forward-backward selection methods, is what's called penalized regression. And I'm not going to go into any detail on how this is done, but basically what we're doing with penalized regression is we're going to apply a penalty that shrinks regression coefficients towards 0. And so what we get then is a elimination of less important variables, and the more important variables sort of come to the surface as non-zero regression coefficients. And one of the kind of interesting things about penalized regression is it doesn't matter how many predictor variables you have in relation to your subject. In fact, you can even have more variables than you do subjects. So we have 46 demographic, clinical, echo, morphologic, CMR, genetic, and biomarker variables that we began with. And so we applied our penalized regression to each of the 10 imputed data sets. And then for each of the 10 data sets, we ranked the variables according to their order of selection. And so for our initial model, we used the predictors that showed up in all 10 of our imputed data sets. And so this is probably more detail than anybody wants to see, but one thing I want to point out here, when we ranked the variables that they showed up as far as or appeared in each of our 10 data sets, you can see that index LA volume was always the first one in all 10, and contractile percent was the second one selected in all 10. After that, it's sort of varied, but it turns out that of the variables that were common to all 10 data sets turned out to be 11. And so these were the two that were always selected in all 10. The rest of these showed up and appeared in all 10 data sets, although not in necessarily the same order. So we chose these 11 variables to look at as far as predicting atrial fibrillation. The rest of these showed up less than 10 times, so we didn't include these in our initial regression equation. So our statistical analysis, I mentioned, is Cox proportional hazards regression. We did that for each imputed data set. But one of the other things that we needed to consider is the notion of a competing risk. And the reason for that is if you have a particular outcome, then to get the incident rate or the survival rate, there might be other events that would affect this. And in this case, death is considered a competing risk of atrial fibrillation. Because if a person dies, then they have no more chance of experiencing atrial fibrillation. Now, if they had an AFib before they died, then that's, we can count that. But if they died before experiencing an AFib event, then they're, in a sense, they're out of the consideration for having an AF event. So there's a method for dealing with that. However, it's also controversy regarding that. And I won't go into why that is. But so we compared the fine and gray method with just censoring at death. In other words, when we did the time to event Cox model, we just censored with death or censored at death. So then the estimate we're going to get is the regression coefficients, and then what we're going to use is was a question that was asked earlier in the first hour, was we're going to use the information criteria, Kaiki's and Bayesian information criteria, to choose best model. And so the next thing was to compare the competing risk model with the no competing risk, or just censoring at the time of death, or censoring when they died. And it turns out the regression coefficients were essentially the same. This is just for one of the data sets. I did this for all 10 of them. And you can see that the differences in the regression coefficients that we estimated were pretty small. So based on that, we then decided that we'll just do the Cox models and censor patients at the date of their death, rather than doing the competing risk model, because that's obviously more difficult to deal with. So we're then going to do the Cox proportional hazards model for all 10 data sets, censoring patients at either their time of death or when they were lost to follow up. So the another issue, and I think this is the final issue I had to deal with, is when we do survival analysis or time to event, the assumption of the Cox model is that hazards are proportional. And what we mean by that is that over time, the proportion, or the ratio of the hazard rates are essentially the same. And you see this by looking at, say, the survival, a graph of the survival functions, and if they look like this, they're more or less parallel, then the hazards can be considered proportional. If the lines cross like this, then we have non-proportional hazards. That is, the hazard rate is not the same over the time period that we're looking at for different groups. So you can see there's a lot of issues that we had to think about in doing the analysis. So when we put this all together, and then of course we did a multiple event analysis, as well as an analysis just to the first event. So we had 96 patients, as I mentioned, with 127 events. 85 had one event, 6 had two, 2 had 3, and then there were 1 each with 6, 8, and 1 patient with 10 events. So, and I just wanted to give you an idea here of when you have a situation where you have multiple events, the data would be structured something like this, where for each patient you would have a start time, that is their either their entry into the study, which is time 0, and then when they have an AF event or whatever the event might be. So here, the first patient had an event at 12 months. So there's just one row for this, and this is an age, and MR is mitral regurgitation. So patient 2 here had an event at 15 months, and then at 27 months, they had a second event. So we have an indication here I've called order. So they've had 2 events, and then patient 3 had 3 events, the first at 6 months, then at 18 months, and then at 31 months. And so that's how you organize data when you have multiple events. Okay, so then after we get our model, then we're going to look at model discrimination, which has an index that's called a C index. It ranges from 0.5 to 1, where 0.5 is none. You have no discrimination between those that experience the event and those that don't. And then calibration, we want to look at the agreement between the observed and predicted outcomes. And we do this by looking at a regression with slope equal to 1, or whatever the slope is, 1 being perfect calibration, meaning there's perfect agreement between the observed outcomes and the predicted outcomes, whether it's a mean or a probability or whatever it might be. So it turns out that in our analysis that the proportional hazard assumption was not met. And it turned out that age was the contributing factor to non-proportionality, as there were significant interactions of age with index, LA volume, LA is left atrial, contractile percent, and BMI. And so in our analyses, then we stratified by age. And out of the 11 variables that we started with, we wanted to then see if we could even reduce that to an even smaller set, because the smaller your model or the more parsimonious your model is, the better it is. But it has to predict, the reduced model has to predict as well as the full model. So we do this by what's called the likelihood ratio test, whether the reduced model is comparable to the full model as far as its ability to predict and discriminate. And I've given the formula here for the likelihood ratio test, which is the log likelihoods, the difference in log likelihoods times a -2, and that's distributed as a chi-square with degrees of freedom equal to the number of parameters in the larger model minus the number of parameters in the smaller model. I'll show you where that statistic shows up in the output. So it turns out that for all 10 data sets, if we look at just the time to the first event, then we have 5 variables in our model: BMI, index, LA volume, contractile percent, mitral regurgitation, and history of arrhythmia. And age, of course, is significant, but because it's non-proportional by age, then we're going to stratify by age. And so these other variables then were dropped from the model. The multiple event model included the same as the first event, except for the history of arrhythmia. And then, as I mentioned before, we estimate the regression coefficients for a single model by combining results over the 10 data sets. So here's the initial output for all the 11 variables that we started with. And so we have the number of subjects. This is time to first event. So we have 96 events. And we have this statistic here called the log likelihood, which I'll show you how that enters in a minute when we compare models. And so you can see that some of these are statistically significant, some are not. But what we want to do is we want to see if we can eliminate any of these variables here and still come up with a model that is just as good as this one. And we're going to do that by comparing these log likelihoods. So you have to make a decision on which ones you want to eliminate. So one way of doing this is taking the ones with the largest p-values here and eliminating those. So the history of afibrillation, we might take that out, or the reservoir percent. But basically what you're going to do is take out one at a time, see what you get, and then see if you can take out another one and then another one and come up with the most parsimonious model. So this is the model that I finally came up with, where we had 5 predictor variables. And you can see that this includes BMI, history of arrhythmia, contractile percent, left atrial volume, and microregurgitation. And you can see that history of arrhythmia here, although the p-value is not significant, if we take that out of the model, then it turns out that it's not as good as the model with it in the model. And so what we're going to do then is we're going to compare this reduced model with the model with 11 variables in it. So our -2 times the difference in log likelihood. So this is 345. You remember the other one was 342. We get a value of almost 6. And if we compute the chi-square that has 5 degrees of freedom, because we had we had 10 variables in the full model and only 5 here, so we have 5 degrees of freedom. So that turns out to be the p-value 0.46, so or 0.47. So that tells us that this reduced model is just as good as the model with the well, I guess it'd be 10 variables because we're stratifying by age here. So so we can then use the reduced model here as our model, that our best model, and then we compute the regression coefficients by average over the 10 different data sets. So then another issue that we had to think about was, then how do we present these results so that it's understandable? So because we're stratifying by age, one way of doing that is to break age up into groups. So you might do this by tertiles or quartiles or quintiles of age. We use what's called splines. I won't go into any great detail here, but it turned out that if we have a spline with cutoffs at age 32, 52, and 62, which turned out to be the 10th, 50th, and 90th percentiles of the age distribution, then we used those age groups to plot our AFib-free functions for each of the variables in the model. And so this is a table of the different variables for the time to the first event. So what we have here are hazard ratios. And so what this means is, for example, like BMI, which is stated as 5 kilograms per meter squared. So it has an odds ratio, or a hazard ratio of 1.38. So what that means is that for every 5 units increase, for every 5 units increase in BMI, the probability of, or the hazards of experiencing an AFib event are increased by about 1.4 in the overall model. And then so what I did is to look at each of the age groups that we have. And so you can see that for the youngest group here, although there aren't very many in there, very many events, the hazard ratio is actually over 2. So that means it's for the younger group that is the hazard for experiencing an AF event is increased by over 2. And then the same interpretation for the rest of the variables that are in our model. And then so our overall model is pretty good. The C index is 0.75, and our calibration index is quite good, 0.94. So of course it's different and sometimes less or more or less for the different age groups, but this was included in the table to illustrate the differences of effect of the variables, BMI, volume, contractile percent, so on, by age. And so, for example, you can see here that for BMI has hardly any effect for the older patients. That the hazard ratio is essentially 1, so that means that there's really no effect for the older patients. And then this was the table for the multiple events, so that turns out to be fairly similar in terms of interpretation. Again, there's basically for overweight younger patients, there's a higher hazard or higher risk for an AFib event than for older patients. And by the time you get to 62 or over 62, there's hardly any impact at all. And so we then ended up showing graphs, which, as they say, a picture is worth 1,000 words. And so for a graph, survival graph for each, or not survival in this case, but AFib free for each age group. And so you can see that for BMI at the younger age, it's pretty similar, although as we saw, there was a bit of a drop in the hazard for overweight younger patients. You can see more separation in the 33 to 52, and the 53 to 62, and then here is plotted greater than 62, and so is the hazard ratio indicated that was nearly 1. You can see that there's hardly any effect of BMI on being AFib free, since the curves overlap. The AFib free curves virtually overlap here. And then this was for volume. So again, at the younger age, there was hardly any difference here. You can see the big drop here if they have a high volume, left atrial volume. The AFib free is much less than it is for smaller values of volume. And this continues through the other age groups, although the effect is not quite so great for the older patients. And then for contractile percent, which is actually in the positive direction, the smaller the contractile percent, the worse is the greater the hazard for experiencing an AFib event. So here for contractile percent being 25%, you can see that there's greater hazard, and that really emphasizes or shows up much greater in the older patients with a smaller contractile percent than the other age groups. And then I think finally, oh yes, and so finally what I end up with here is what is known as calibration plots. This is where I want to look at the observed versus the predicted. That helps to establish the validity of my model. And so you can see that for the different variables in my model, that there's really pretty good agreement between the observed, which are the solid lines, and the dotted, which are the predicted, and then for different values of, in this case, like BMI, I did less than 25% or greater than 30%. So you can, I mean, they're not perfect, but there's really pretty good overlap here between the observed and the predicted. So that gives you, I think, a flavor for how complicated and how any particular analysis can be when you want to do prediction of a particular event, whether it's in this case the event and time to event, or if you look at just events, an event in general that occurs in a particular time frame. So there's a lot of things that may have to be considered, and particularly when you have non-randomized studies, which is this is. So it can get quite complicated in the different things that you need to look at. You have to really pay attention to them. Whereas if you have a randomized study, then the statistics are pretty straightforward. They might involve time to event, but you would have just, you know, the time to event functions for one group versus the time to event functions for another group in a randomized study. Okay, so I will stop there. And I guess we want to take a break here. You want to take time for a few, are there any questions?
Yes, yes. So we have some questions in the chat.
Okay.
I think in our case, we have the coding aspect. So John was saying we should go a little bit into the coding side and see how much the recording will take. So let's see, currently we have 137. We end at 2. So I don't know, unless you guys have any questions, we'll just keep going through the coding section and for the next 10 minutes and see how far we go. Okay, so the coding section will be the same as with the other one. Let me let it go.
Yeah, so as William is saying, if anyone has any questions, yes, if anyone has any questions, you can ask the questions now, and then he will, again, as I said, the recordings are there for you to review them. But if you have any questions at this time, you can ask the questions, and then William will play William, since you are on, I think someone asked a question about in the chat area about the office, no, not the office, about the office hours, right?
Office hours. Yeah, so we plan to have one tomorrow. So I'll link up with Chelsea for the URL, and it will be on Slack. So normally, if you go to Slack, let me see if I can come out of here. If you go to Slack, you'll see that there will be TA office hours, and there will be a link here, and there's also going to be a link in general. Yeah, so there will be a link if you look in the, and so we'll get in touch with Stacy and provide a link.
Yeah, so anyone, if you've registered for this training, then you should have access to Slack for this training. So you go to Slack, and then you can go to the Slack anytime and then see any announcements, or you can even post questions there.
Yeah. Okay. So yeah. So we'll do that, and let's go back to our time here. In the absence of, I think we'll do it here like that. Let's see. Okay, go. I didn't get it at the right spot. I was trying to get it at the right spot. Yeah.
Okay.
Yeah, let's reconvene at 1:10.
Okay, thank you. We'll see everyone at 1:10.
Okay, let's give it a little time, and then it's going to pop up. And I'm going to give it a little. I don't want us to lose. There we go. Still coming, still coming. Okay, I think we'll take it from here. Okay, so we can all see the screen, right? I have it shared. Let's see, new share. And I'm going to share this one here. 3D, this one. Okay, is it being shared still? Yeah, it's being shared. Okay, so is it all set? I can't hear the voice. That's the. Now give me a second. Let me stop. And let's try it again. Because it's not coming through. I don't know why. So let's try share. The sound is on. And we're sharing the 3D.
So as William is getting this fixed, I just want to add that, William, this is using Cordio, right?
Yeah, this is using Cordio, yes.
So those of you who are not familiar with Cordio, the live section starts next week. Cordio will be used, and then you have access to Cordio, and then you'll be able to practice some of these things as the training continues. So you have access to Cordio. Everything from next week will be live, so you can actually do some of the things as it goes.
Environment's up to date. And if you're using Cordio, the Cordio files are up to date, so we should be fine.
Excuse me, I saw another question here about timeline to develop a model. So that really varies. This was quite complex, so this took quite a bit of time. I can't remember exactly how many months, but it would have taken probably 3 to 4 months to develop that. And then after I actually developed the model, the PIs, the principal investigators thought, oh, you know what, we left out a variable. So I had to do everything all over again. So, you know, things like that happen, you know, too. But yeah, it's not just a matter of, you know, a couple of days. It takes some time too.
Okay, now let's see. So the voice is not coming through. That's it. So let's see. Let's give it a little time. The voice is not coming through. Yeah, John, for some reason, the voice, the audio, I'm not hearing any audio on this part. Let me go down a little bit.
This time it's not clean, it's cool. And if all goes well, it should bring the data. So it tells me it's up to date, so I'm fine. Okay, so that's the first thing you want to do. So we give everyone a minute to try that out. And then once you have it, then you open your Anaconda and point to this directory, the 3D directory. And then there will be a file in there called mod3b day 1 -2 exercise. Okay, so that's what we want to open. If you open that, then you will get something that looks like, so let me kill this guy and kill this guy. You will have something that looks like this here. Okay, so primarily, you have this open one of the files, and in your case, you are going to open the exercise. Okay, how do you know is the one that we want, you see that it's code along student file. Okay, there will be a solution file in the solutions. As usual, when you get stuck, you just look at the solution file. You work on the student file, and I will demo using the instructor file. Okay, and the instructor file tells you here. So why don't we take 5 minutes? Everybody, make sure you have your file where you have your files open, and then we move on. In Codio, it's the same. You go to your Codio folder, and then when you click on the file that says exercise mod 3B day 1-2 exercise, and that will give you something that looks like this. Always look for the student. It will tell you whether it's a student file or it is. So there's a student file. So we take 5 minutes, and then we come back. So get yourself to the state, and then we should be all set. If you're on your personal laptop, then run this portion. Okay, take out the exit. Okay, put a pound at the exit. If you're on Codio, don't do that. So on Codio, don't do that. So let me move this out of the way so I don't confuse the Codio guys. The Codio guys, you're all set. The non-Codio guys, you click on the libraries, and then in here you put a pound, and then run it. Okay, and run your segment. And so we take 5 minutes and get back. Ball. Okay, so let me emphasize that if you go to just mod 3, you won't find anything. You have to be in the mod 3B, like ball. Okay, so check out the GitHub. I made that clear, but if you didn't catch that, yeah. So if you go here, you see there is a mod 3, and there is a mod 3B, like ball. And that's 5 hours ago. This is 7 days, so that's 1 week. You want this folder, okay? And then these are the 2 files that you want to open. Okay, so in the interest of time, let's keep going. Okay, so primarily what we're going to do here is you have your file open. We're going to try and mimic most of the tables that Paul had gracefully provided, the data, and I give you the slide number and things like that. So specifically, if you take a look at this slide, okay, this is what Paul used. If you go a little up, you see things like that. And so we want to replicate these models and these tables in Python. Okay, so that's what we're going to do. So you load your libraries, and then once you finish loading them, you put back the exit so that next time you run, it doesn't reload. I mean, because the install takes time. Okay, so then this part here is just a warm up, just to recall what Dr. Musa did with us, what the different types of Python data types are. Okay, so just take a look at how the data types are, because we'll need this as we move along. We need to know how to create a string. We need to know how to create an integer, a float. Okay, so these are just here, FYI. Okay, so if you run this, you see an output. What I look out for is how to display my result, how to create a data frame, how to create a dictionary, and things like that. And how to play with the import, because we're going to use a lot of math functions. So where those functions are. So if you take the ln, the natural log, it's in the math function. If you want the power, it's in the numpy, okay? And then you can compute some values and print those values. Okay, so that's what we're doing in here. Recall that if you don't have certain libraries you're going to get an error. I have the numpad in my environment, so it's not going to give me any problem. If you, on the other hand, this is the first time you're doing that, then you may want to, after you install, you may want to import. Okay, you may want to bring in these the libraries that you would use. So you bring in something like NumPy and pandas from Dr. Musa's class. Okay, so run this, and you'll get something like that. Don't worry, if you didn't get an error, just as a warning. Then you'll be able to run this. Okay, so then you'll be able to run this portion and observe the output. So this is just observation. And then the actual task starts here. Okay, you have 5 tasks for today. And so please just follow this and just fill in those, the ... has to be filled in. I've given you the output. So primarily I have a list and I want to create a data frame out of it and display it. If you do it right, you get this out. Okay. If you struggle with it, then you go to the solution. Okay. So just go to the solution and you would have the solution in here. Okay. If you're on Codio, the solution has been separated. The solution has been moved into another folder.
So that's
So
okay.
you would click this one.
Okay, cool.
And
Okay,
you'll
let me do
see that it's an instructor. And then it tells you how, or you can even run it in the instructor window. And
okay, so yes, so I think that we have a lot of materials in here, and I don't think we have enough time to go through, but the materials are very self-explanatory. Just go to the GitHub site. Okay, go to your GitHub site, download the file. If you have any problems, we'll have a TA session on Saturday. But in the interest of, let me see if I can get my file up.
you will get,
Oh, sorry. Let's see this. Okay, here. So if you go here and you go to any of the Google site, you'll see the videos. Okay, you see these videos in there. You also get them from our site. So I'm going to post this here. And the GitHub site, let's see if I can get you the GitHub, because someone said it, but I think it's already there. Let me see if I can get the GitHub site. Otherwise, just show up on, yeah, I don't think I have it here. Okay, let's do, we'll end it, and then if you have any questions, just post it on the Slack. I'll post the link on the Slack as well. So I'll pass you over to John.
William, someone also said, how can you show us how in Slack? I guess they don't know how to use Slack, or are you able to quickly demonstrate?
Yeah, let's do that. So in Slack, what I do is,
if you can share your screen so they see.
Okay. So let's do that. Share. I'm going to share this. Okay, so what I do is, depending on, you can get Slack online. Otherwise, Slack is just like, let's put it this way, like WhatsApp, right?
Now, William, if they click on the link that was sent to them, won't that take them to Slack?
Yes, it will take you to Slack, and it will Slack will also say, hey, do you want to install a local version? So if you go down here and you go www.slack, okay, or you go Google and say download Slack, okay, and then you go here and say download Slack, okay, for Windows, for Mac, you go down, and that will take you to a place like this.
Are you trying to show something? Because I don't think anything is shown on the screen.
Oh, sorry. Let me share again. Okay, now is it showing this time? Oh, let me stop share and let me try sharing again. Sorry for that. Thanks a lot, Stacy. Let's see. I'm going to start sharing. So I'm sharing this window and share. Is it showing now?
Yes.
Cool. Yeah. So what I was trying to show was this one here. So assuming you went to a Google site, you say download, okay, download Slack. Then the download Slack will take you to a Windows page or a Mac page. Okay, I'm going to put it right here. So in here, you can just log in, you can sign in, or you can get a local version. It's always better to get a local version. Okay, so if you don't have a local, then you sign up for Slack for free, and then next time you can sign in. Now, if you get a local version, then what you would do is you start it just like you start any application on your Windows platform. I always start as an administrator. You don't have to start. You just click and it opens it up like that. Okay, and since you sign up for Slack and you're a member of this VADSTI 2.0, it's going to show up. If you are part of any, if you sign up to any channel, any discussion group, just like Twitter does, you're going to see these other groups. So I'm a member of this BSU, I'm a member of this, I'm a member of that. But the one you want is the one that says V2, this one. And then once you come in here, you are now going to see all these channels. The one that you want to pay attention to is the general. This is where Stacy will post the TA session. And then I duplicate that here. Okay, I duplicate that here. But we have multiple channels that you can basically go and chat. So let's say I'm here and I'll just say, hello, TA session, for Saturday. Okay, and then I'll post the URL. And so once I do this, you will be able to see it if you subscribe to the Slack. Okay, and if I want to send something to someone specific, then I go down here and I look for the person. So far I think I only see Nana, Stacy, and I don't think there's any of the students. Yeah, I don't see any of the students in here. Oh, I see 2 students, right? I see this other person, right? So please sign up and then your name will show up here. So then if I want to send Stacy an email, I just go down here and this will go to Stacy's status like that. Hello, Stacy, like that. Please send me the TA link. Okay, and then Stacy can, so you'll see this. This will be a direct communication between you and Stacy. Right. So that's how it is. It's very easy and easy to use. And then you can see other people that you communicate with. But the channels are the most important ones, the TA and the general.
So in addition to Slack, from next week going, as I said, you have the opportunity to actually practice some of the concept that will be delivered to you live online. So you use what we call Codio. And I believe, William, if I'm right, if you don't have Codio, you still be able to do some of the things. I mean, from what you were saying that we said, okay, those using Codio, those without using Codio. So what would be the advantage for everyone to use Codio?
Yeah, so the thing with Codio is a web-based, right? And you have all the libraries will be pre-installed for you, but it's a web-based, which means you need internet connectivity to get to it. If you use VS Code or you use your own version of Anaconda, which Dr. Musa took us through, so if I have Anaconda and I fire up Anaconda, then you would have your own local version of the IDE running. Okay, so this is VS Code and this Anaconda coming. So this one here is VS Code. And as you can see, I see everything that was shared with you. The interface might look slightly different, but it's primarily the same functionality.
So in other words, using Codio, then many things to make things faster, easier and faster for them, because many of the things will already be loaded there. So they don't have to start from the scratch.
Exactly. That would be the advantage. But the thing too is that once you leave the class and you don't have, once the class is over, well, we have to talk to Nana about that, the logistics of Codio, whether they would have it for the rest of the time. Otherwise, the Jupyter Lab, Jupyter Notebook will be the way to go, which is what Professor Musa did in this class. He used a local version. Yeah.
Okay, so we'll end here, and again, thank you all for coming. Please check on the survey and then complete the survey for the pre-training sessions. And then next week, we'll see you all for the live session. So prepare yourself, get ready. The recordings are there for you to review anytime at your own leisure times. You want to do that. If you have any questions, then you can access next week, or you can post your question in Slack, and then someone will answer you from there. Any questions, any final thoughts from anyone before we end for the week and then reconvene next week? Any questions for anyone? All right, so if there are no questions from anyone, then thank you again all for coming, and then we'll see you all next week, same time, Thursday and Friday.
Thank you, and bye-bye. Thanks. Bye-bye.